okay? All right, are we ready for some touch on PDEs? It's just like a 5-minute lecture, very quick. It's just worth having the slides with you. And Rachel? Yes, no more homework assignments. There was a rumor that there's like 1 or 2 more homework assignments. No, there's no more homework assignments. Okay, but it's very important that you do this last homework assignment. I know you're overwhelmed and you have a lot of other courses going on, but I can tell you as a person who is creating the final exam for you, the last homework assignment is very, 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 to the power n as n approaches infinity, very relevant to the final exam, okay? So try to work it out. The examples and the slides for the ODEs are very, very important, okay? All right, partial differential equations are when you combine boundary value problems and initial value problems together, and you get partial differential equations. So in other words, you're combining an initial value problem and a boundary value problem. Then you have to specify initial and boundary conditions. Partial differential equations, as far as we understand intuitively, describe things that vary both in time and in space. So take that lobster. Oh, I had a joke about the pizza, that I'm not getting any lobsters also for that Tuesday. I know someone requested that. I should have made that joke during, anyway. Okay, so if you take that lobster's temperature as it's cooked, we assume that the entire lobster is being cooked at the same temperature, and the entire lobster temperature is changing at the same time, just over in time. However, there might be a change across the lobster. Let's say you're grilling it. The side that's closer to the fire is exposed to more heat, and as the heat comes through and penetrates the lobster, right, there is also a change in temperature within the lobster itself, right, in space. So all practical real-life situations are best described by partial differential equations, a change in time and space. What I'm showing here is one very complex heat equation described by temperature here in a general reacting flow. You have a time derivative and you have spatial derivatives. Now this nabla operator, the inverted triangle, that's called the nabla operator. That's a vector operator that operates in 3 dimensions. You know, there's gradient, there's divergence, there's dot products. This is a very complex equation, describes a lot of things going on. For example, this term is a rate of change in temperature at any point in space. This term describes convection of the temperature, which is the motion due to the presence of a fluid flow. As you see by that u velocity vector, that's the velocity vector that's the speed essentially of the fluid flow. This term describes changes in temperature due to the pressure, because in a gas, pressure and temperature are tightly related. This term describes changes due to viscosity, so the ability of a gas or liquid to resist motion. As it resists motion, it heats itself, so that's friction essentially. So this term describes that. Then there is changes due to thermal and species diffusion and chemical reactions and temperature and chemical reactions and radiation and other sources. So as you can see, partial differential equations can be very complex. This is the type of equations that we solve in my research group. Okay, this is just one simple equation, in fact. But it's not that difficult to solve partial differential equations if you know how to solve ODEs. It just requires you to do a leap in your thinking into combining the spatial discretization with the discretization in time, as we will see in a minute. PDEs are further classified into 3 general types, ambiguously called hyperbolic, parabolic, and elliptic. Whoever, the mathematician who came up with that classification is picked like the most horrible nomenclature. Hyperbolic equations essentially describe events that where information is only propagated in one direction or another direction or in both directions, and they only depend on what's happening previously. So, for example, if I have a pie, I'm baking a pie over here, and I have a fan over here, and the pie is, emitting its smell, and then the fan blows on the pie, right? So that wind is gonna take that concentration of the pie smell and move it in this direction. So over here behind the fan, you can't tell that there's a pie over there because you can't feel it. Okay, if you were in a dark chamber and you can only smell things, you can't tell that there's a pie over there. So in a way, you have to be in the path of motion of that information. Okay, so here's an example of a hyperbolic system. You see, this is the initial condition, and that initial condition is just moving in one direction. Now, as opposed to parabolic equation, with parabolic equations, you have somewhat of a diffusive process. A parabolic equation or a parabolic phenomenon, like the heat equation, tends to take an initial condition and try to distribute the information everywhere. Okay? In hyperbolic systems, if you have a discontinuity in your initial conditions, that discontinuity is going to be preserved. Okay? In parabolic systems, if you have discontinuities, generally those discontinuities will just dissipate. There's another feature of parabolic systems, and this might be kind of problematic to think about, is that information in a parabolic system propagates at an infinite speed, or in other words, at the speed of light, if you want. So if I were to take this phenomenon, whatever is going on here, like a heating in temperature, and I heat it, change the temperature a little bit, everywhere that temperature change is going to be almost instantaneously felt, as opposed to this guy here. If I inject some new information here, a point here is going to have to wait in time for that information to pass through. The final type of partial differential equation is called elliptic. These are typically stationary problems. In other words, these are things that do not change in time, only change in space, such as a boundary value problem. So the boundary value problems that we solved for the heat equation, the heat transfer in a rod, that's an elliptic problem, okay? And strictly depends on the boundary conditions, okay? An elliptic problem, think of an elastic rubber band or an elastic rubber surface, and you pinch it at one point and just propagates everywhere. So every point in the domain is going to affect every other point equally. Okay, so there's no preference in one direction or the other, right? Now, the classification comes from the coefficients in the partial differential equations and what they mean to conic sections. So if you take a cone, slice it horizontally, you get a circle. If you slice it diagonally, you might get an ellipse or a parabola or a hyperbola. That's kind of the classification where it comes from, okay? But this is just a synopsis, okay? I'm not teaching you PDEs here. I'm not expecting you to learn all of this, just to expose you to the complexity of the potential of things you can learn, okay? The classic example for hyperbolic equations are wave equations or advection equations, okay? A wave equation is nothing more than two wave equations combined with each other. So when you throw a rock in a pond and you see those waves propagating and bouncing back and forth, this is an example of a hyperbolic system. Parabolic systems almost always have a diffusion term present, and the diffusion term is always described by a second derivative in space, okay, not in time, second derivative in space, okay? And finally, elliptic equations. This is pretty much the standard elliptic equation, which is the Poisson or Laplacian or the Poisson equation, which is nabla squared phi or del squared phi equal to s or some source term, okay? There are numerical methods for partial differential equations, just like there are for ODEs, and the idea is to convert the PDE into a system of ODEs, and then solve that system of ODEs, and then proceed, okay? So for systems which have a time derivative on the left-hand side, like d phi by dt, first you convert into a system of ODEs by taking the right. So remember, with ODEs, we said we had our canonical example, d phi by dt is equal to some right-hand side, okay? The PDE, a PDE is no different than that. It's d phi by dt equal to a right-hand side, but the right-hand side has spatial derivatives in it. So if we were to discretize the spatial derivatives first, So that's going to give us couplings between point I plus 1, I minus 1, I plus 2, I minus 2. What that means now is that at each one of those discrete points, you have that same PDE, which becomes an ODE actually at each one of those points. And then you discretize in time with forward Euler or backward Euler or Crank-Nicholson or whatever, and then you have a system of ODEs. Yeah? No, that's still ODEs because you're only doing change in time, right? So maybe not on the home, but yeah, maybe in the homework, the boundary value problem, if I add a time derivative to it, du by dt, for example, then that becomes a partial differential equation. You're not only tracking change in space, but you're also tracking change in time, or make the space in 2 dimensions or 3 dimensions, x, y, and z. It doesn't matter, but it's easier to explain discretization in space first, because that gives you a right-hand side, phi I minus 1, phi I plus 1, and the time derivative is at I, as you'll see in the next couple of slides. And then you'll see the system of ODEs, which you can just solve with directly, okay? For PDEs that don't have a time derivative in them, so a steady state or a stationary PDE, like the elliptic PDE heat transfer problem or the boundary value problem you saw on your homework or in class, but in 2D or 3D, in 3-dimensional space, then you also do the discretization, but now you have x, y, and z. In other words, you can index with I, j, k. For example, you have I plus 1, j plus 1, j minus 1, and so on. And you'll get a very, 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 very large system of linear equations or nonlinear equations if the PDE is nonlinear itself, okay? So it's really not that big of a leap. It's just there's more record keeping because you have more indexing you have to keep track of, more arrays you have to keep track of, you have time and 3 space dimensions, so that's a lot of things to keep track of. Okay, we'll start by looking at parabolic partial differential equations. The standard equation is a generalization of the heated rod problem that we did in class. In the heated rod problem, we only had d2t by dx squared. Now, if you were to take that into 2 or 3 dimensions in x, y, and z, so like heat in a cube, for example, or a sphere, right, then you have the Laplacian operator, which is d2t by dx squared plus d2t by dy squared plus d2t by dz squared. So that you have all 3 space dimensions. And then you add a time-dependent term to it, so now you have a change in time as well, okay? So here's how we do this. So first we start with the spatial discretization. So I'm giving an example here in 1-dimensional physical space, okay? But we still have a time derivative, so it's still a PDE, okay? All right. Can we reduce the chatter a little bit, please? Okay. So now if you were to take at a point I in space, so you take your space domain, this is still a rod, okay? You take the space domain at any point I, we've seen this, it's phi I minus 1. You discretize the right-hand side, phi I minus 1 minus 2 phi I plus 1 over delta x squared. The source term is just a source term. It's evaluated at point I. Then what you've technically done is you've discretized the PDE at an arbitrary point I. Now, that right-hand side plugs in directly into the PDE, but the time derivative now is the time derivative at point I, okay? So now at every point I from 1 to n, you have an ODE d phi I by dt, okay, equal to this entire right-hand side. So if you split that, this is what you get. At the first point, you have a boundary condition. At the first interior point, you have d phi 2 by dt equal gamma phi 1 minus 2 phi 2 plus phi 3 over delta x squared, and then so on. d phi 3 by dt is coupled to phi 2 and phi 4, and so on and so forth. So you have a system of coupled ODEs now. So we converted one PDE into a system of ODEs, and now the ODEs are solved as a system of equations. Now, you can just plug this into ODE int and let it do it for you. That's generally inefficient. We typically write our own discretization for this entire system. We convert also all of these guys using forward Euler or backward Euler and then solve the system, okay? So in other words, what you've done now, you've added one more dimension in time from time t to time t plus delta t, okay? And I'll show you some examples with some solutions. This is, for example, this heat transfer in a rod, which changes over time. This is the initial temperature at time T1, and then as the temperature decays, like you've seen also in that second or third slide, you see kind of how the heat is being dissipated and transferred through the rod. There's a few more animations here. This is a problem with Newman conditions at the right-hand side. Oops. But you see the change in time and also in space. Now, here's an advice for you. Don't plot these things in 3D. Like, don't plot the temperature versus time and space. It looks like a 3D surface, but it's useless to visualize. I really like two-dimensional plots. But here I have an additional dimension. So here I have space on the x-axis and the value of the temperature on the y-axis. You know, my 5-year-old could interpret this probably. But I have one more dimension, which is the animation, right? That animation is showing me the dimension in time, okay? So use color, use animations to describe any higher dimensions if you can, okay? That's a little tip for visualization. This is another example of heat penetration through the ground throughout the seasons, okay? And as the outside temperature cycles throughout the year, and the heat is penetrating into the ground with a certain heat transfer coefficient. If you are looking into the ground, surface temperature all the way to like 20 meters down into the ground, you see kind of how the heat is propagating down into the ground throughout the year as a yearly cycle. And this is the PDE that describes that. It's the same PDE I showed you in the previous examples, but the boundary conditions are different. If you've taken partial differential equations, you will learn that a PDE only has a unique solution when boundary conditions are specified. And each boundary condition is going to give you a different solution than compared to any other boundary condition, okay? Hyperbolic partial differential equations or wave equations, they're some of my favorites, but they are actually very hard to solve numerically. They look benign over here, but this term actually is what gives rise to shock waves, okay? Is what gives rise to shock waves in real life. Anyway, but here's an example of a wave equation. At the top, I'm showing an experiment of a plucked string. And at the bottom, this is one of our codes where we were implementing a new method for wave propagation to show you, to try to compare to that plucked string. Pretty cool when you see it in slow motion, right?
It's a Fourier series summation of the individual standing wave patterns on the string. After several cycles, the pronounced kink has disappeared, and the motion looks much more like the entire string simply bounces.
So this is a numerical calculation of that problem, and shown also in slow motion, right? But if I were to speed that up to real time, it would look like that other string. Anyway. So we can do this. And finally, elliptic partial differential equations. They're a different animal, but they're just a boundary value problem. Like we did in class, we had a system of linear equations in the x dimension. If you add y and z dimensions, it's no different. You have to discretize in all of those directions as well. So for example, for the two-dimensional Poisson equation, del squared phi equals some source term, this is the discretization now. You have points in x and y, and we index those as I and j. So at a point ij, you apply the discretization for each one of those terms. You get coupling between I plus 1j, I minus 1j, and then ij minus 1, ij plus 1, okay? And then you fill out that entire, this entire space domain, and you get a very large system of equations, okay? It's still linear in this case. And then you just kind of solve the system, right? You have a very large system of equations. It's no longer tridiagonal now. It's actually pentadiagonal. And so you have five non-zero 5 non-zero diagonals, and it's solvable. We solve that all the time. It's a this is a very popular equation. And that's it. That's all I have for partial differential equations.